So yeah, thank you very much for this the invitation to participate in this event. This has been really interesting. A lot of very interesting presentations from the other members here, and thank you also for the audience for sticking around for this third part. I can see already plenty of familiar names from our steering group, some other previous colleagues as well. So yeah, thank you very much. It's been really interesting to be a part of this event. Today I'm going to talk about some results and the main motivation behind the COSI project. How was the development of this co-simulation platform and some preliminary results that we have obtained so far. My name is Sergio Motta, as Monica has mentioned. I'm the research team leader of the Smart Grids team at VTT, which is the Technical Research Center of Finland. And just let me see if I find here my proper mouse and passing on the slides. So yeah, today that we're going to tackle what were the motivations behind this project, why developing this co-simulation platform, how did we define this platform architecture, how we can fit in the models and perform the simulations, perform the testings there, and some preliminary results on some fault-based studies. And we will conclude with what is still yet to be done, what is the future work, what are the next steps for the COSI platform. So yeah, why create this co-simulation platform? It was very interesting mentioned by Kevin in his presentation, the report on the electrical simulation studies from the NEA. And it is rather interesting to see how electrical simulations typically are very much decoupled from the thermomechanical and reactor physical simulations in nuclear power plant operations there. And yeah, so the objective and the motivation behind this project is to mitigate this decoupling, is to try to increase the communication between two different simulations, and in that try to produce more robust and more accurate results of the actual behavior of the nuclear power plant operations during grid events, and what would be the behavior of the transmission systems and the power systems themselves with different operation modes in the nuclear power plant. So we want here is to avoid this black box thinking that we typically have in our simulation studies for power systems and nuclear power plants there. And so the name of the project is the co-simulation model for safety and reliability of electric systems in a flexible environment of nuclear power plants. And here's why the name of it is COSI. So we aim to produce a co-simulation platform there. So this platform integrates on-site electrical power systems, off-site high voltage power systems, so the transmission system models there, and also the thermomechanical, reactor physical automation models within the nuclear power plant boundaries there. And this co-simulation platform can be used for evaluating a great number of aspects in this interaction there. So we can evaluate the adequacy of the safety requirements that are within our regulations. We can verify whether our nuclear power plant operations meet those requirements, what sort of impacts grid disturbances may have on the behavior of nuclear power plants, what sort of impacts those nuclear power plant operating modes or flexibility scenarios, for instance, may have on the transmission system side. And in our group here, in our research group, we are focusing mostly on the power system side. So we are, again, not looking at the nuclear power plants as a black box, as we want to avoid, but rather focusing more on the on and off site transmission system and evaluating events there and how they reflect on the nuclear power plant operations. COSI has been a really collaborative project it is funded by the Finnish Research Program on Nuclear Power Plant Safety, SAFIR 2022, and it has been going on since 2019. So it's a continuation project that has been evolving throughout the years, and it has counted with the support from many different partners and with a very active steering group there as well, which we really appreciate this feedback. So developing such a complex tool that tackles so many moving parts is a rather complex task, and therefore it needs a very high degree of collaboration. So the COSI project has been really collaborative, and the feedback from the industry has been greatly appreciated, because after all, we want to produce a tool that is used by the industry by industry experts to really assess the questions that you may have. So how does this development of the platform has been going on throughout the years? So we look to combine the thermomechanical simulations with the electrical simulations through a master file there. And this master file was developed in MATLAB programming language, and it acts as an OPC client that connects both the electrical models and the thermomechanical and automation models. Uh, the latter are modeled in our cases here in APROS, the simulation software, and we can also integrate other electrical simulation softwares such as Simulink, PSCAD, and so on. So at the moment, we have been focusing mostly on looking at Simulink for the electrical side and APROS for the thermomechanical side of nuclear power plants. Uh, so yeah, the main goal here is to establish this communication and data exchange between the simulations that occur in two different softwares. This master file, as I mentioned, was developed in MATLAB, but there are future plans to take it for an open source language, such as Python, for example, or C, in order to make it as accessible as possible. And we also want to support different electrical simulation tools. So modeling the nuclear power plant operations in APROS, but also including the on-site and off-site, perhaps transmission systems in PSCAD or Power Factory, PSSE or something like that. It depends on the feasibility of integrating these simulation tools. So yeah, so we want to link two simulations for a more complete overview of nuclear power operations and safety assessment. And since I'm Brazilian, it's pretty much mandatory that I make some sort of football analogy at some point in this presentation. So the COSI behavior, the operation in the COSI platform is similar to that midfielder. We just get the ball from the defense and pass it to the attack. So nothing fancy. We don't do any tricks or anything like that, but we just ensure a proper link between the two stars of our team here, which are the thermomechanical and the electrical simulation side there. And plugging in those models, that's one of the most important aspects that we have. We typically use already existing models developed in those platforms there. So nuclear power plant models modeled in APROS, they were supplied by our partners or in our steering group. The on-site grid models, they were also supplied by our partners and modeled in Simulink. And the offsite grid models, they were initially considered as Thevenin equivalents of the transmission system, but we identified the need for the development of a more robust model ourselves. So that is also something very, very interesting and rather important that we have been developing in the COSI project. A step-by-step user manual is already available for indicating how to plug in different models in each one of those simulators that we link. So it is somewhat easy to just plug in different nuclear power plant models, different on-site grid models. They are already in our platform. As I was mentioning, the transmission system model that we have been developing ourselves with a lot of support from FinGrid, we transferred from Thevenin equivalent of the transmission system model towards an 8-node model, and later on towards a 50-node model for the Finnish grid. This work has been done by Aalto University, our partners in the COSI project, and it's been a really excellent effort by our partners there. This transmission system model is a extremely useful, let's say, byproduct of this COSI project. So it was not our main goal, but since it was identified that we would need such a model to effectively have more accurate co-simulations there, uh, those efforts have been really justified, and we have been able to produce very good results with the transmission system models there. So testing this platform through those fault-based studies, was our main goal for this year. So as I mentioned before, the project has been going on since 2019, where we defined and implemented this platform architecture. In 2020, we tested this co-simulation platform architecture and performed the first tests with basic models. And in 2021, we really dug deep into it and implemented some very large nuclear power plant models. We upped the scale of our models that we are using in the platform, and really performed some stress tests into our architecture to notice that it did pass those tests. The communication between the two simulations has been working as we expected. The plans for 2022 are to perform other types of studies, so looking at different future grid scenarios, which is also quite linked to some of the presentations that we had today in this workshop. And we also want to develop this open source platform for increasing our the extent of people that we can reach with the platform there. Yeah, as I mentioned, the tests and simulations, they focus more on the electric grid side and how it affects the nuclear power plant operations. So we planned for 2021 to perform some fault-based studies on the on-site and off-site electric grids. And so far we have we have implemented the on-site faults. So the off-site are a work in progress as of now, and by the end of the month we will probably have already some results on the effects of off-site electrically close and electrically far locations from the nuclear power plant. So for the fault-based studies in 2021, we have defined 6 priority locations, both on the on and off-site grids. We defined which fault types and which parameters to evaluate, and we selected different fault scenarios for comparing between a co-simulation and a purely electrical simulation. In that way, we were able to evaluate what was the benefit of a co-simulation model in different scenarios there. So for those on-fault scenarios that were implemented, we have used a basic on-site grid, so just a generic on-site grid there with some locations specified. Fault location, for instance, we performed the scenarios, the fault scenarios were a 3-phase short circuit at the low voltage side of the unit transformer, the same type of fault at the low voltage side of the auxiliary transformer, and also open phase conditions at the output of the main generator and also at the low voltage side of the auxiliary transformer. And we were able to evaluate what kinds of effects those fault scenarios had on the generator output, for example, or the pump behaviors in this basic nuclear power plant models. So just as examples here, I will not go into too many details of how those faults were simulated or the behavior that we observed. Just some comments on the benefits that we identified from the co-simulation compared to the simulation. That once we evaluated the main generator active power output for a short circuit lasting 250 milliseconds, so a longer fault than the required than the clearing time that is required. So in that case, the protection system has failed to clear the fault at the required time for any particular reason. And we noticed that the purely electrical simulation, which is the blue line here in the plot, recovers quite quickly to that situation, whereas the co-simulation considers the instability also in the automation control and the thermomechanical processes in the nuclear power plant, and has a slight delay on recovering properly there. This behavior was not observed in faults that were cleared within the regulation time, so less than 200 milliseconds of fault durations. Both curves behave exactly the same, but once the protection systems start to fail or fail for any reason, we do see the benefit of the co-simulation there. So that is one thing to keep in mind from our presentation. Similarly, we can also observe the behavior of the torque in one specific pump at the nuclear power plant there. And with an open phase condition at the main generator output, with a purely electrical simulation, the torque stabilizes after that fault. Whereas in the co-simulation, it shows that the torque remains falling way after that fault has been cleared. So the inclusion of those constant updates that come from the APROS side to the electrical simulation really produce very different behaviors there, and gives perhaps a better overview of what is the expected behavior of different components in the nuclear power plant operation. So yeah, what sort of benefits does co-simulation bring? Because performing a co-simulation, it does indeed, it is more computationally expensive. It does take a little bit longer because you are indeed running two different simulations at the same time. So it has to bring some sort of benefit. And this benefit doesn't come in every single case. So it is important to notice which cases do benefit from that. So one specific case in which co-simulation does indeed produce uh, benefits, and it is warranted the use of this sort of platform, is to analyze border cases when the protection systems do not work or they do not clear the faults at the designated regulation times. Also, the modifiable time steps that we have in our platform, they allow for transient analysis in electrical systems from that are caused from disturbances from the mechanical side, and also the possibility to plug and play, quote unquote, already ready-made simulation models to evaluate the different impacts is also rather beneficial. So instead of utilizing a generic model for a transmission system or on-site grid or a nuclear power plant, we can indeed evaluate the specific impacts of grid faults on that specific nuclear power plant, for example. So it brings a bit more information about the safety and safety assessment of that nuclear power plant. And the platform has many other possibilities. So it shows a lot of potential for different use cases. It was developed so that we can analyze the behavior of any different entity in the nuclear power plant, in the on-site grid and in the off-site grid. So the plots that we obtain are very easy to modify, and which variables will be plotted, which variables would be considered. It is fairly simple to define itself by the users. Different fault scenarios, such as the very interesting presentation that we had previously for EMP cases, for example, they can also be implemented in the Simulink models to produce the impacts and behaviors in the APRS side, in the thermomechanical side. So the possibilities really are rather endless there on different fault scenarios that we can test. And the in-depth behavior and the in-depth analysis of this nuclear power plant behavior it is somewhat out of the scope of this project itself. Like, we want to focus on creating a functioning platform, but we have been counting with some excellent feedback from our steering group, and we are able to really evaluate whether those faults are impactful or not, and that has been also another interesting result from the project. So yeah, just to conclude and list some of the next steps, so to watch this space in a sense. The development of the project continues, and we have identified that, of course, that the better and the more detailed models that we have, the better the results output from the co-simulation, which is a fairly obvious conclusion there, of course. Since we are not simulating anything ourselves, we are counting with the simulation in the APROS and the Simulink models. So more robust and more detailed models in each one of those software produce naturally better results there. This co-simulation platform can be a very interesting resource for designing and modeling the protection and backup systems, specifically at the on-site grid. So it provides some valuable feedback on that specific aspect of nuclear power plant safety assessment. And yeah, we have identified that in these fault-based studies that perhaps fast faults or fast clearing faults may not be the best use case for the co-simulations. So perhaps just electrical simulations are indeed already enough in that aspect. However, it may be very well interesting to look at slow and systematic changes, such as a varying energy mix in the transmission system, for example. And this is one of the plans for the continuation of the work. And yeah, so we are still a long way from a complete and final tool, but it is now at a very usable state, and we are very confident that it is working as intended, as to say. The communication between the two simulation platforms is working well, even with large models, and yeah, and the possibility to add these new electrical simulation softwares and to transfer this platform to an open source. It is a very promising also potential situation there to improve our reach there. So yeah, with that we close saying that we greatly welcome the feedback that we have. We greatly welcome the interaction with industry experts to tell us what sort of aspects you would need in such a platform, whether you think that we are in the right path or not. And yeah, now I open up this space for some questions and some comments, and I'm very looking forward to it. Yeah. So thank you very much.
Thank you, Sergio, for an excellent presentation. And to everybody, please raise your hand or write your question in the chat. And while you do that, I would like to ask you, Sergio, would it in any way be possible to compare the simulation to a real case with data from a plant?
Yeah, that's a very good question, actually. I think that since we are always dealing with data vectors in those types of simulations, it would be very well possible to compare actual fault measurements with the results that we have. And unfortunately, we don't have access to those types of data in this year of the project, but the continuation work, we have indeed proposed that this could be one thing that we would look at to really validate our results against real world data. Yeah.
Yes, and hopefully that would also further enhance the importance of having the co-simulation.
Yes, absolutely. Absolutely. We do hope for it. Yeah.
Any other questions to Sergio? Matthias?
Question or rather a statement, but I'm just realizing that maybe there is an opportunity for liaison with the benchmarking activity on electrical simulation in the WG Elect that are just starting up now. I'm aware that this might be the first time you've heard the information that this is ongoing, but do you think it's a feasible or even useful activity that you might undertake in the coming year to try to calibrate the modeling methodology that you're proposing here?
Yeah, I think that that would be a rather interesting opportunity for us as well. I think that we aim to have this tool the more robust as possible, and I think that this sort of opportunity would really help with this sort of goal. So yeah, thanks for that comment.
Thank you.
Great. Any other questions? Or perhaps a comment. I think that there might be some people in the COSI steering group that are in the meeting here. If any of you would like to comment. Everybody's too shy. Sophia?
Well, I'm not in the COSI steering group, but I could add, since we can take advantage of earlier presented work, maybe that we could use the fact of looking at the high frequency events, maybe slow events that raise the power in the grid, and how that affects the power plants could be interesting to use in the COSI project. So we can continue that discussion after,
Yes.
but that could be an option.
Yeah, absolutely. I think that I am very hopeful that the future for the COSI platform is a bright one, and I think that there is plenty of things to evaluate here. So yeah, thank you for that comment. That is indeed the case.
Thank you. And Parlamel, do you want to comment anything from the steering group?
No, I think it's very good that you see that you can benefit a lot from this tool in long time events. Actually, that's maybe a little bit waste of computer effort actually for the faster events actually. So that's very good that you can see that it will be interesting to see actually where is the borderline more or less for the tool when it's reasonable to use this type of tool comparing to a normal electric dynamic simulation tool. So for the event, so if it is possible to find out a number or something like that, or
Yeah, that is again another very good comment indeed, and we have been discussing this with our steering group. With Per has been giving this sort of feedback to us, and it is indeed very greatly appreciated. We completely agree that indeed in some cases the co-simulation is not justifiable for such short-term events there, but we really wish to see whether those long-term events bring some benefit from the co-simulation. Yeah.
it's an interesting project in that way, actually, to put these two different kind of tools together, actually. So, and today I'm sitting in a group with these two tools. So for us, it's very incredibly interesting, actually, project. So in that way.
Yeah, thank you very much. We had some very good project managers that are attending in this call from before. So yeah, that's much appreciated as well. Thank you very much.
So maybe these former project leaders can join the discussion forum at 4 later on. Great. So thank you very much, Sergio.